Welcome to the COVID Q&As. Oh, wait. Bit misleading. Okay, I understand. Welcome to we had to change our teaching format because of COVID Q&As. So, all jokes aside, hope everyone is happy, safe, doing well. Hopefully your families are doing well also. As you all know, in-person classes have been suspended because of, we want to stop the spread of the COVID-19 virus. However, the show must go on. Still got lots of learning to do, and so we're going to continue. Now for all my classes except this one, Math 1206, I am still just recording lectures and posting them on YouTube and dealing with questions that arise from those lectures already. However, since I'm not actually recording 1206 this semester, it felt weird to start recording lectures to me in the middle of the semester, so what I asked you guys to do is to watch previously recorded lectures of 1206. So I recorded a couple of classes of 1206 back in spring 2019. So I sent you guys a playlist to watch. I will link that playlist down in the comment section, the video description. I said that so often to put questions in the comment section. Like this is like the third lecture I'm recording today. I will put that playlist in the description. I asked you guys to watch a video. Really, you should have been watching 3 videos for this week, but I think I only told you guys to watch 1 so far. But I did have some students who actually went ahead and watched 3 videos. So I asked you guys to watch lecture 21, but of course, technically we're supposed to have 3 classes today. So if we're really good boys and girls, we should have also watched lecture 22 and 23. If you haven't watched them yet, that's fine. Just watch them by Sunday, I would say, and submit your questions to me by Sunday. Because technically I think spring break starts on Monday, so let's try to get a solid week in before then. So because I'm not actually recording lectures for you guys, what I thought I would do is instead just record some Q&A sessions. So if you watch a lecture and you have questions, I ask you to send me your questions about the lecture that I asked you to watch, and I will deal with them in a specially recorded Q&A session. So if this Q&A session generates more questions, you can drop those questions down in the comment section, or you can email me through Jupiter Grades, as I mentioned. If you're a student of mine, emailing me at my regular college email at the moment is just kind of, it's going to be easy for me to miss things because a lot of things are in flux. I'm getting emails from all over the place, from administration, from other teachers, from students, just about how we're going to deal with this situation that we find ourselves in. So I don't want your email to get buried if you email me directly to my college email. So just send me an email through Jupiter Grades if you have questions about the lectures, or drop them in the comment sections if you don't want to remain anonymous, if you don't mind not being anonymous. Or hey, you could make up an alias and drop the question down in the comment section, and I'll answer it in the next video, like math student _3142 asks. Okay, so I do have a couple questions from you guys, and yes, some students are asking questions from lecture 23. Let's start out with the lecture 21 questions though first, and I'll hopefully uncover some issues there. Oh jeez, I just touched my face, I messed up, already messed up. Okay, so lecture 21, I believe, was the lecture where I spoke about linear approximation and differentials. So let's deal with a couple questions there. Have a question from one student saying, oh, I understood the majority of the lecture. It's just that when you have to pick your own values for the equation, I'm not sure if there's a very specific value that I have to pick, or if any value is okay. Is there flexibility here? He also asked, what equation you have to use. So let me kind of remind you guys of a context here. the problem would be something like me asking you to approximate the square root of something like 3.99 with linear approximation or something like that, right? So the wording is going to be similar to this or whatever, right? So how we set this up, you might remember, if you watched the lecture you'd remember, is we chose a function that's going to track something, then ultimately we're going to choose x equals 3.99 and a equals 4, and we're essentially going to want to use the fact that f of x is approximately equal to f of a plus f prime of a times x minus a. Right? So this is the linear approximation formula. And so the idea is we have something that we don't know what the exact answer is, and we want to approximate that answer without a calculator because this is Calc 1. And so we track it with a function that we can approximate with the equation of the tangent line to that function. Okay? So the question that he basically asks is, so this would be the question. So nothing I write below here will be given to you. You had to know all this. So the question that he's asking is, how do I know what value I should have picked? How would I know to choose the value 4 here? Or did I have to choose the value 4? Could I have chosen something else? Also, he asks, how do I know what function to actually pick? In terms of there being flexibility, there really isn't, kind of. Technically, you do have some flexibility in the function, but again, even there's kind of something that you want to look for to have less work for yourself. But how would he know to choose the a equals 4? It really is the only choice, so there really isn't a lot of flexibility here. Remember, the goal is x is the value we want to approximate f of x at, right? Well, what is your a? Your a is a value close to x for which we know what f of a is and what f prime of a is, right? Now again, this is just a Q&A session for a lecture, so if you didn't watch the lecture, you're probably totally confused about everything I'm talking about here. So if you are totally confused, what you need is you need to go back to that playlist. You need to watch lecture 21, linear approximations and differentials. I explained it from scratch, but just to pick up with the question. So you notice that the value that you particularly care about is evaluating a square root at 3.99. You need to come up with a value close to 3.99 for which you already know what the answer is to the square root question. You also will know what the answer is to the derivative evaluated at that point. Notice that this would mean that your f prime is going to be 1 over 2 radical x. So you're going to pick a value that's close to this, that you know what the radical of it is, and you know what 1 over 2 times the radical of it is. 4 is really the only choice here. So there are a lot of numbers that we know how to find the square roots of. We know how to find the square root of 0, of 1, of 16, of 9, of 25, of 36. We know a lot of square roots, right? 144. However, only one of them do we know that is close to 3.99, right? 4 is the only answer that we know. So technically, while you could have chosen like a 9 here, you would not choose a 9 because you're not going to get as good as an answer. The farther you're away from the number is the farther away you are from how how good your approximation is going to be. So there really isn't much leeway in terms of choosing the 4 here. 4 is really the only answer that actually makes sense for you to choose. In terms of the function, then yes, he also asked, would you just replace that constant with a variable? Usually, yeah. So the function, remember, is we want a function to be able to approximate something like this. Since we want to approximate the square root, of some number, some random number, the square root function is what we could use. If we evaluate it at that number, we get that. So yeah, you are going to make your function kind of look like the thing you want to approximate, except where that weird number shows up, you are going to want to put a variable. I could have asked other things. So if I were to ask, for example, say, approximate the tangent of 0.01, right? So now, guess, what would your f of x be, what would your x be, and what would your a be? Right? Just to see if you can get, so this is using linear approximation. So, pause the video. This is just testing if you kind of saw where I was coming from, if you understood what I said last time. Pause the video, give it a shot. Okay? I'm going to assume that you paused the video. So, if I were doing this problem, f of x equals tangent x would be what I would choose. My x is, of course, 0.01, because tangent of 0.01, I have no idea what that is. The 0.01 is the kind of the weird thing. And of course, what is something that's super close to 0.01 that I know what the tangent of it is? Well, 0. I know tangent of 0, so that would be something I would pick. It's also worth mentioning that the derivative here would actually be secant squared. And I also know what the secant squared of 0 is. So that's a good thing to pick. So these would be the choices I would make in this problem. And of course, I'm going to end up plugging it in to the formula f of x is approximately equal to f of a plus f prime of a times x minus a. If you're interested for this particular problem, this will be tangent of 0 plus secant squared of 0 times 0.01 minus 0. Tangent of 0 is 0, secant squared of 0 is 1, and so this ends up just being equal to 0.01. 0.01 would be my approximation. But yeah, so you choose the function to kind of mimic the thing that you want to approximate. Of course, you're going to replace the variable with, replace that weird constant that you don't know how to deal with a variable. And that's it. Here's another one, just as a quick one-off. Approximate, say, the sine of pi over 6 plus 0.01 by linear approximation. If that was the question, tell me what your f of x would be. Tell me what your x would be. Tell me what your a would be. Pause the video and tell me what you think. Okay, so hopefully you attempted that. The best option here, in my opinion, would be sine of x. X would be pi over 6 plus 0.01, and my a would just be pi over 6. That would work nicely. An okay option, but less efficient, I would say, would be something like the following. Set your f of x equals to sine of pi over 6 plus x. Then I can set my x equals 0.01, set my a equals 0. That could also work. That's less efficient though. So, so to strictly answer the question, no, your function doesn't have to look like a very specific form. But there's really only one form that's going to give you the least amount of work to get to the answer. So both of these setups will actually get you to the same answer, and you'll be able to make an approximation for both of them. But that one's a lot nicer. For one, this one, to even start calculating what that's going to be when you start plugging in stuff, you might have to do a chain rule for the derivative, and in certain contexts, not in this one, but you might have to find the addition, you have to remember the addition formula for sine to figure out what would sine of pi over 6 plus this be, right? So something like this is probably how I would do it. this is a weird value. I can see the sine function is what I want to approximate. I need to approximate it at this value. Just replace that value with an x, and that's my function. Then that value is obviously what I want to be able to talk about. And my a is a value super close to this. That's nice. It's a value at which I would know what the sine of that value is. And I will know what the derivative of sine evaluated at that value is. The derivative of sine is cosine. Sine of pi over 6, you should know what it is. And cosine of pi over 6, you also should know what it is. So that is that question for linear approximation and differentials. Let's see, let me log in here. Yeah. So hopefully that answers that question. Another question from I notice linear approximation and differentials both come down to the same question. Does this mean they are the same thing? And if they are not the same, what exactly are differentials? So they both use the same idea, but they're not exactly the same thing. The differential is a part of the linear approximation formula. So in the sense that they're very similar on one end, they're not exactly the same thing. So when you look at something like you have y equals f of x, when we use the Leibniz notation to talk about the derivative, dy dx equals f prime of x, it turns out the guys on this side, these guys are called differentials. This is called the differential of y. This is called the differential of x. So the differentials are usually the duy. So dy equals the differential of y. So a differential, what it actually is, it's just a differential. It's an approximation for the change in y. Right? So this is the tangent line approximation for the change in the y value. That's called differential. Now according to this formula, you'll notice that if I were to solve for dy, I would get f prime of x dx. Right? Now it turns out that dx is actually always equal to delta x. So you can always think of it like that. And you can normally think of your delta x as just the change in your two x values. So it'll be something like a minus x. So when we write the linear approximation formula, how it usually looks is f of x is approximately equal to f of a plus f prime of a times x minus a. This part of the formula here is dy. It's the differential. Right? So a differential is just a part of the linear approximation formula. They really are the same thing. The differential is what you get when you isolate the change. The linear approximation starts out with the old value plus the change to give you the entire new value. If you just focus on the change only, you say you're focusing on the differential, the difference between the two. The tangent line approximation between the actual value and the approximated value. So that's how the differentials are the same, kinda, but different. It's just one, the differential is one part of the linear approximation formula. You can think of the linear approximation formula in this vein. It's like whatever the old y value was, this is whatever the new y value is, this is approximated by the old y value plus the differential. Right? So the linear approximation formula uses a differential in it. So that's the difference. Another question was, Yeah, this is from the end of lecture 1. There was an example where we're talking about, oh, there's a cylindrical can and we wanted to measure a change in volume. Use differentials to find the change in volume. So at the end of there was a problem where we know the bottom volume, which is pi r squared h, and we wanted approximate the change in volume. This means we needed to find the differential dV. And a question comes in here. The student asks, okay, for the example at the end of lecture 21, it seems the solution would kind of be using multivariable differentiation to solve the problem. But what about linearization? I don't know how to use the differential idea to solve it. That is actually an insight that is actually a couple semesters ahead of where we should be. Yes, there is a nice multivariable calculus interpretation of what we're talking about, meaning something that you would see in a calculus 3 class usually. So, kudos to the student who actually saw that this was something from Calc 3. If he knows about Calc 3, I'm not sure what he's doing in Calc 1 class, but whatever. I digress. The idea was to actually go through and take derivatives of both sides. dV equals 2 pi r, differentiate the r. Of course you have dr plus leave the r, differentiate the h, then you have dh. The differentials equation would look like that. And that does look like one of the things that you would see if you were doing the chain rule in Calc 3. Now, why is it that we're allowed to do this in Calc 1 using differentials? That would be the answer, by the way. And the way you want to think of it is basically as implicit differentiation. So kind of thinking of what would this look like if you were to differentiate, for example, with respect to t. Just for example, since we've been doing problems like that. You would get dv dt equals, you do the product rule, differentiate the r, so you get dr dt, leave the h, plus, now you leave the r, differentiate the h, you get dh dt, right? So that is what we would know from implicit differentiation. It actually works here, just an application of the chain rule. Now what you can think of is just multiplying both sides by a dt. So we essentially cancel the dt from both sides. This leads us here. So you can kind of multiply by dt. Now the theory here is beyond our scope, but essentially the Leibniz notation is very functional. You can kind of use it as a fraction some of the times. Strictly speaking, some mathematical purists do not like that way, that idea, but in practice, that's how things are done a lot of the times. And that kind of connects implicit differentiation, which we have covered in Calc 1, to what that would look like. By the way, I did answer this question in the very next lecture. So I know I didn't ask you guys to actually watch that lecture, but if you went to lecture 22, I actually covered this idea. So in the beginning of lecture 22, I started going through this problem and someone asked a very similar question and I actually explained to them, oh, you can think of this as an implicit differentiation idea. How much time do we have left? Well, this Q&A session is actually turning as long as a lecture is. We're almost half an hour in. So that was another question from lecture 21. So think of it as an implicit differentiation idea. You can differentiate. If you have two variables, yes, you have to do the product rule, think of them as one function at a time, and you just attach a differential whenever you differentiate a certain variable. So that's how that one would end out. So lecture 21 ended with this question, but it didn't go into the solution. I actually did the solution in lecture 22, and I explained that idea. So watch lecture 22, and hopefully that plus what I just mentioned might help clear some things up. So I had a student go ahead and talk about, ask me a question about lecture 23. So in theory, this student watched lecture 21 and 22, and they're on lecture 23, which technically is where we should be up to. And so this is in the same playlist that you see down there, but lecture 23, not 21 this time. At 21:50, 21 minutes 50 seconds, I'm confused when you find the critical point for tangent. What do you do with those for secant squared x dx and y? I'm a bit confused at that point. So this is kind of jumping ahead of the gun because it's really not something that was dealt with in lecture 21 at all. I think I started dealing with this towards the end of lecture 22 and it spilled into lecture 23. So there is the idea of a critical point that we will be talking about pretty soon. So there are things that we call critical points of some function f of x. And basically the definition of this is points at which f prime of x equals 0 or undefined, right? So if you want to find the critical points of a function, what you do is you find its derivative, then you set the derivative equal to 0 or undefined, and you try to solve for those points. So there was a problem where I asked the class to actually find the critical points of the tangent function. Now how we did that was we find the derivative, secant squared, and then what we want to do is we want to set secant squared x equals 0 or secant squared x undefined, right? And so, yes, the problem is really focusing on the tangent, but all the groundwork is going to be done with the secant squared. So that's why I think that was a little bit confusing for the student, because they didn't understand. Why are we doing all this work with secant squared? I thought the question was talking about tangent. Yes, the question is about tangent, but the critical points of tangent are determined by how its derivative behaves. The derivative is secant squared. And so secant squared equals 0, we know that's never true. This is never true. So there is no such point. However, where secant squared is undefined, there is actually such points. This is 1 over cosine x, right? So this is undefined when cosine equals 0, which means your x is going to be n pi over 2, where n is odd. And so these guys here are critical points for tangent, right? So like plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, etc. So that's why we did all this work with secant squared, because to talk about a function, the critical points of a function, we determine that from how its derivative behaves. So if I want to talk about the critical points of tangent, I need to actually talk about how does secant squared behave? When is it 0? When is it undefined? It's never actually 0. However, it's undefined every time a cosine hits 0, which happens at all odd multiples of pi over 2. So that's what we were doing there. There's another question by the student, but I think she just missed me simplifying something and canceling 2's. So I'm not going to go into that. I think I already emailed her back about that. Yeah, and another question was, I spent a lot of time on test 1. So this isn't really about the lecture actually. This is just a general question, which I think I do want to address here. I spent a lot of time on test 1. I didn't do as well as I'd hoped. Is there any hope? Is there anything that I can do to make up for the points I missed? So, a lot of students might be worried about their grades right now, not only just like in a general sense, but just because of what's been going on with the coronavirus and schools closing down and things like that, and it's really kind of hard to see how we're going to make up a lot of things. However, I will say this, in general, I'm not really the make-up kind of guy, in the sense that I know there are some teachers who when you do bad on a test, they give you a makeup test, or they give you another test for the whole class to do, or they give you some extra credit to kind of make up that grade. I don't agree with that logic per se in general, because I think it gives you wrong expectations for the class and just for life in general, if I'm allowed to be a little bit philosophical here. Sometimes in life, you do something, you work hard, you prepare for it, and it comes around, the day of reckoning comes, and you don't do as well as you had hoped, and life didn't turn out the way you wish. It turns out that there is no rewind button. You can't do a makeup, right? It just doesn't happen. Sometimes things don't work out you want, and you can't just redo them on the spot and make everything okay, right? You're training for the Olympics, you've been working hard for 4 years. You go to the Olympics and you don't get a medal. You run a race and you come in 4th place. You can't have that race being done over right on the spot. Oh, the 4th place person said they want another shot. Let's redo it. Let's redo the race. It does not happen. However, life does afford you the opportunity to learn from your mistakes, to examine yourself, what you did, what you could have done better. If you did anything wrong, how can you make it up for the future, not necessarily for that. So while I'm not going to talk about makeups for test 1 specifically, I do believe in rewarding students for improvement over time. So if you end the class strong, to me, the stronger you end the class, the less messing up on test 1 or any previous quiz is going to matter. So in that sense, I would say categorically, in general, for everybody, it is still possible for anyone to get an A. So don't even worry about you passing the class. You getting an A is technically still possible. So I'm not going to say it's going to be easy. Some of you might have so far have a really bad grade and you have to do a lot of work to get to that point. But if we're at the end of the semester and there's a final exam, whatever form that's going to take now, I'm still not sure actually. But I realize on the final, you're getting everything right that was on test 1 that you messed up. To me, it's like, I'm not going to judge you so much for what happened back then. Right now, you know what's going on, right? So it's like, I am currently reading the paper of an A student. It does not matter to me that 2 months ago you were a D student or you were an F student. Right now, you're an A student. And if that's the case, that's what I'm going to give you. If you can show me that you improve over time, that's what matters to me. So, not that technically there's a do-over for test 1. Your test 1 is what it is. I'm not going to change that. But there is benefit for you to improve over time. And that is also not as realistic as life would be. Sometimes you mess up and you can never undo it, no matter how much time passes. But I think that's a better way of approaching learning, which is supposed to be in a low-stakes environment. That's a much better way of approaching it in a way that will help you not only be better at the class, but be better at life in general. Don't think you can just undo mistakes, snap your finger and undo something. But if you do mess up, there is hope. As long as there's life, there's hope. Work hard towards a better future. Don't get bogged down by your mistakes of the past. Right? Look at it with an objective eye just to understand, here are the things I did. I could have done this better. I did this totally wrong. And change. Put in the work. Try to change your trajectory. Try to end up somewhere better in the future. And yeah, that is it, I would say, for now. So, good luck with everything. Stay safe. Don't go out if you don't have to go out. Wash your hands for at least 20 seconds very often. Yeah, keep sending me questions. So, I would say I would like you guys to watch 2 lectures. Watch lecture 22, which is the one after linear approximation and differentials. So watch that one and watch lecture 23, which I believe some students try to get those watched by Sunday and get me some questions in by end of day Sunday. Then you can take a break Monday. There are some people that I was supposed to be meeting with for office hours. Obviously, that's not happening this week. But since today, Fordham set up like a corporate Zoom account, so each department in each professor or lecturer in each department has their own Zoom account now attached to their Fordham account. So I'll be using that to set up office hours in the future. So office hours in the future are mostly going to happen through Zoom. So I'll give you guys more information on that. That just got set up today. So sorry for the delay there. Other than that, I think we will stop there. We're about 35 minutes in, it seems. And yeah, that was a good Q&A session. Stay safe, send me more questions, keep studying, keep working hard. If you've done bad on test 1 and the quizzes, do not give up. Always trying to improve, always try to become better every day. That is what life is about. We all mess up sometimes. I've done it. Every single human being has done it. Don't get bogged down by that minutia and let that weigh heavy on you. Pick up the pieces, look at what you did, look at what can be better. Meeting with me during office hours can help you to determine what are some things you can do better for the future. But as long as you improve over time, you know, Jhevon is going to work with you to put you in a better position. That being said, I'll see you guys in the next one.